Bismillahirrahmanirrahim. Good afternoon, everyone. Today at this lecture, we will solve another question. This question talking about doped semiconductor, silicon semiconductor. Here, determine the position of the Fermi level with respect to the intrinsic Fermi level. That means this question will be different from the last one. Here, the Fermi position, that means EF, will calculate the relation, will calculate the distance between the EF and the EFI, that's means intrinsic Fermi level, in silicon at room temperature. That doped with boron. The boron, I explained the important information about this element at the last lecture. Boron has 3 electrons at the last shell. That means will attain to take 1 electron from another neighbor silicon to can build its wall to can be more stability. That means we will dealing with p-type semiconductor. And Na, that means the concentration of acceptor at valence band equal to dot exponential 16. B, repeat part A, if the silicon is doped with phosphorus atoms at a concentration of Nd. I will explain the difference between this situation after when I solve the unfinished part A. I will explain the important information and what it's different from the last one. Let's start to solving part A. Here, like I said before, is doped with boron. That means we're dealing with p-type, and p-type by using mass law. That means N naught, P naught, the concentration of electrons, concentration of holes equal square intrinsic carrier concentration. And here with p-top, P naught, concentration of holes equal the concentration of acceptor at valence band. The most important thing here, in p-type, the diagram will be different because like we know, we have 3 important lines. The first one, conduction band, at the middle, Fermi level, at the last, at the bottom, the EV, the valence energy band. Here, we will have a new element. In p-type will be Efp, in n-type will be Efn. I will explain this information by using the diagram that will be clear to us. Okay, now let's say EFI, intrinsic Fermi level, minus Efp, Fermi level to holes to Fermi level, the same thing, equal KT ln concentration of holes divided on intrinsic carrier concentration. Now let's thinking about why. Let's just wondering why EFI minus EFP. Why not EFP minus EFI? Because this diagram will answer us here. Because EFP, because we're dealing with p-type doped, that's right. EFP we will drawing this line EFP near from EV, valence band, far away from conduction band, near from valence band at p-type doped, because that will be EFI from above minus EFP. This we will use this way, okay? Now let's complete. KT at T room temperature, we know equal 0.0259 ln concentration of acceptor divided on intrinsic carrier concentration at room temperature, we know 1.5 exponential 10. This is the last result, but I don't know. In internet, when I was researching, I found another student solve it, but with another result. I solved this by myself, and I don't know the student found this result. Don't know, maybe the mistake from me or from him. Okay, let's complete. This is the important diagram, like I said before, and we will find the N nodes and P nodes at the twice side. By using the mass law, N naught dot P naught equal intrinsic carrier concentration square. At P type, like I said before, P naught equal NA. Here to find NO, N naught intrinsic carrier concentration square divided on the concentration of holes, and at the same time divide on concentration of acceptor at valence band, because P naught equal NA at P type. The last result, 1.12 dot exponential 36. Okay. Here, let's talk about the same situation, but with doped with phosphorus. Here, when we're saying now we're dealing with another element, phosphorus, all the situation will be different, because phosphorus has 5 electrons at the last shell. That means we'll attain to give 1 electron from these 5 to be more stable, to can be stable, and to can build its wall with the other silicon neighbors. Okay. When I say phosphorus, that means 5 electrons at the last shell. That means we're dealing with N-type doped. N-type doped, that means concentration of electron equal donor concentration at conduction band. That means N naught equal to dot exponential 16. Now, EFN minus EFI. We must note this important. EFN minus EFI. Here the situation is different. Here EFI minus EFP. Why not EFI minus EFN in P-type? Because this diagram, like we said before, here we have 3 important lines: conduction band, intrinsic Fermi level at the middle, at the last one at the bottom, valence energy band. Here, EFN, Fermi electron energy, this line will be near from conduction band and far away from valence band at N-type. And the distance between EFN, the above, from the EFI below, the distance here, this line, black line, EFN minus EFI equal 0.365 electron volt. To find the N-type, like we know, by using the important equation, important law, it is mass law, P naught, N naught equal carrier intrinsic concentration square. That means P naught, like I said before, N naught equal ND. That means 2 exponential 16. To find the result of concentration of hole equal intrinsic carrier concentration square divided on ND. That means concentration of hole equal 1.125 exponential 36. Here at the last, C, what was talking about, calculate N naught and P naught in parts A and B. I solved it actually, but let's talk to it together. Yes. But here we must note another important thing. In P-type, the P naught will be the majority. The N naught concentration electron will be the minority. But we will deal with another situation if we're dealing with P-type. For example, phosphorus doped is doped if doped with phosphorus. That's mean N-type. That's mean N-naught will be the majority. P-naught, the concentration of hole, will be the minority. It's important because another doctors use these words. That's not necessary to say concentration of holes. Maybe use the majority and P-type. That's it. We completed this question. Let's stop this record. Thank you about your listening. Have a good day.